Okay, so let's take an example of just a simple, we've been doing stuff like this, right? We've been solving quadratic equations using the square root property, a quadratic equation where we can point to a single x, we can always solve by just reversing order of operations and isolating that x, right? So what are the steps here to solve for x? What do I do first? Somebody just say it out loud. Just walk me through it here real quick. What am I doing first? Okay, I'm adding 5. Good. So I get negative 2x squared equals 18. Now what? Divide by negative 2. Everybody agree? And so I get x squared equals negative 9, and now I'm stuck, right? This is where we kind of left off last time. I'm taking the square root of a negative number, and so I'm not going to get a real answer, right? You can't. That's one of our rules for real numbers is I can't take a square root of a negative number and get a real result. So I get plus or minus the square root of negative 9. Okay, but we don't get a real answer, but we do get an answer. We just get a different kind of an answer. And so we need to talk about a different set of numbers today that will allow us to get answers for this. Okay. We have to introduce something called imaginary numbers. Okay, now this is a really, really unfortunate name because if you think about the two names that we give the numbers that we use, every number you've ever used up through today essentially has been a real number. Now I'm introducing these new numbers called imaginary numbers. Doesn't that sound kind of fluffy to you? Like these things are, we don't have to take them that seriously. I mean, they're just imaginary after all, right? They're not real. Well, no numbers are real. I mean, let's just get that straight, right? Numbers are just, they're an artificial construct that we use to organize our interpretation of the universe, right? But there's no such thing as the number 5, right? What does 5 mean? You can hold up 5 fingers, but that's a concept. That's not a thing. That's a concept, right? So no number is truly real. In fact, we could extend this discussion, and I'd like to do this sometime. I'm just waiting for a good day, but maybe I'll throw something at you right now. I mean, everything in math is abstract. None of it's real, right? Have I ever asked you guys, have you guys ever seen a line? Did I ask you that at the beginning of the year? Has anybody ever seen a line before? Would you agree? Maybe, right? Okay. Give me an example, somebody in chat. What's an example of a line that you've seen? Okay, but like in the real world, can you give me an example of a line or even a line segment that you've seen? Line on a road, maybe. Okay. What else? Anybody else got something? Tree. Okay. Maybe you could say something like lines on paper. Maybe even something like if you shine a laser beam through some mist, you can see the line that it creates, right? And theoretically, that goes forever, right? Side of a computer. Okay, those are all good examples, but none of them are correct. The answer is no, you've never seen a line. You've never seen a line, right? We can say we see things that are sort of linear, right? We talk about a line in non-mathematical terms, and yeah, I mean, we could say, yeah, you bet there's a line on the road. We call it the road line, don't we? But it's our traffic line or something like that. But mathematically, that's not a line. A line, think about the definition of a line, right? A line has how many dimensions, by the way? So we live in a 3-dimensional universe, right? So something like a cube is 3-dimensional, right? Something that's flat, like a piece of paper, is roughly, I mean, we think of it as being 2-dimensional, right? Or like when I write stuff on my whiteboard, I'm writing on a 2-dimensional surface, right? So how many dimensions does a line have? Hold up fingers. No, the answer is 1. It's got one dimension. Think about an ant walking on a line. An ant walking on a line can only move forward or backward. He can't move up or down or into or out of the room. Does that make sense? He's only got one direction to go. It is literally, no, a point is 0 dimensional. Point is 0 dimensional. It has no size at all. Okay? So a line is 1 dimensional. So that means that a line has no width. Right? Well, there is nothing that you've ever seen in the universe that has no width, right? Because we're embedded in a 3-dimensional, there are 3 extended dimensions in our universe, right? And so you've never seen a line and you never will. But the funny thing about it is we all know what we mean by a line, don't we? This is what's truly, to me, this is why math is just such a beautiful thing, because none of it is real. It's completely abstract. There's not a single thing in math that's real, and yet math is the most potent and powerful and informative way for us to understand the world around us, which is real, right? Doesn't that seem strange that something that is completely abstract and unreal provides the best way for us to understand the real world around us? Bizarre, right? I mean, if you want to know, my background is in physics. So if you want to know if I launch a projectile, a projectile. I said trajectile. A projectile on a certain trajectory. If you know what its initial speed is, and you know that the angle at which it's launched, we can use math to predict exactly where it's going to land, right? So that's pretty real, right? I mean, we just took something that's a real world situation and we applied math to it, and we determined where the thing was going to land. But once again, math has nothing real about it. It's all completely abstract. Okay, so we'll talk more about that. That's a discussion there's some very interesting philosophical almost arguments you can have about math, right? And what math would look like in parallel universes even. That's an interesting one. We got to make sure you guys remind me to talk about that on a day when we were not covering as much. Remind me that we really need to talk some cool math concepts that come up that will just blow your mind. I mean, it's really interesting. Okay, but for today, this idea of a imaginary number compared to a real number, that's a poor choice of wording, because it makes it sound as though one of them is more real than the other, and that is not true. That is not true. Imaginary numbers are just as real and just as useful as real numbers. Okay, they just have the unfortunate name of imaginary number, right? So we define, when we're talking about imaginary numbers, we define the imaginary unit I as the square root of -1. Okay, so a pure imaginary number then is written in the form something times I. So it's going to be something like b times I, where b is a real number and I is the imaginary unit. Okay, so if we want to do something like I want to simplify, let's say, the square root of -9. Okay, if I want to simplify the square root of -9, I'm just going to take advantage of the fact that there is a property of radicals that tells us, and we've already mentioned this once this year, the square root of a product is equal to the product of the square roots. So I could write the square root of A times B as the square root of A times the square root of B. Everybody agree with that? Make sense? Okay, that's just kind of common sense too. So I could write the square root of 9 here as the square root of -9 as the square root of 9 times the square root of -1. Okay, well, the square root of 9 is 3, and the square root of -1 is what we define as I. And so that's my answer, 3I. Okay, let's take another one. let's take something like, let's look at a little more difficult one. Let's take something like the square root of negative 192. Okay, so what am I going to do with the square root of 192? I'm just going to break that into the square root of negative 1 times the square root of positive 192, right? And we know what's going to happen to the square root of negative 1. That's just going to become an I. Agreed? So then all I've got to do here is I've got to simplify the square root of 192 by maybe doing something like couples go out, singles stay in, right? Okay, I'm going to show. When I was doing this last night, I was making this flip chart. I discovered something kind of cool I want to share with you. This is a pretty cool little hack on Desmos to simplify big radicals. Okay, look what you can do here. I'm pretty proud of this. This is a pretty good little trick. You can amaze your friends in college with this trick. So if I want to simplify the square root of 192, whatever number you're trying to simplify in Desmos, you can just make a function that is equal to that number. So let's take 192, for example, divided by x squared. And then I'm just going to make a table out of this. So I'm just going to go up to the gear. And I'm going to make a table out of this. And I'm going to extend this table down. I don't care about negative numbers. But I'm going to extend it down for positive numbers for a while. Now think what this is saying. If x is equal to 2, then 192 divided by 2 squared is 48, right? So the square root then of 192 is going to equal the square root of 2 squared times the square root of 48. So the numbers in the x column end up being the numbers that are outside of the radical, and the numbers in the f of x column are the numbers that are inside the radical. Everybody see that? Let me do here. This will make it a little easier to understand, I think. So, right. So then what this is telling me here, is that the square root of 192 equals 1 times the square root of 192. This is telling me that it's equal to 2 times the square root of 48. Okay? So I'm just going to keep adding numbers, and Desmos does this automatically, right? So this one tells me right here, doesn't it then? This one tells me that it's equal to 4 times the square root of 12. I'm just going to go until I get a number in the f of x column, an integer in the f of x column that has no perfect square factors. Okay? This is such a cool little trick. I'm just really excited about this. There it is, right? 3, the square root of 3, I know that has no perfect square factors. And so there's the simplified version of my answer, right? That's it. This is telling me that the square root of 192 equals 8 times the square root of 3. How about that? Isn't that cool? I just think that's super cool, right? And you can generalize this. Okay, so I put something like, I just put it in the notes so you can remind yourself how to do this. But what's really cool about this also is I could use it to simplify higher roots. Like if I wanted to take the cube root of 192 and simplify that, well, all I've got to do is define the function as f of x equals 192 divided by x cubed. And that's where I would stop, right? What's that telling me? The cube root of 192 equals 4 times the cube root of 3. That's pretty cool. Give me 1 to 5 on that. Does that make sense? Okay. Good little trick. Okay. So we know, like, we could now do a problem. Like we could go back, for example, and finish this, couldn't we? Right? We know that we got the answer x equals plus or minus the square root of negative 9. Well, we can simplify this, streamline the process a little bit, we know that the square root of 9 is going to be a 3. And anytime I have a negative inside the radical, that's going to become an I outside, isn't it? So I get plus or minus 3I. Those are my two solutions. Okay, give me 1 to 5. Does that make sense? Okay, good. All right. So we'll skip that. We don't need to do another one of those. All right, so now let's look at different powers of I here, right? So let's walk through this list. And I want you to see that there's a pattern that develops. So I is defined as the square root of -1. I to the 1 is just I. Well, I squared would be the square root of -1 squared. The squared cancels the square root, right? And I get -1. That's important, right? So I squared is equal to -1, okay? I cubed, we could rewrite as I squared times I, and I squared is just -1, so that just ends up being -I. And I to the 4th, we could conveniently write as I squared squared, right? Just using properties of exponents, so I'd get -1 squared is 1. Everybody agree? Does that all make sense? I buzzed through that kind of fast. Give me a 1 to 5. Is that good? Any questions on that? Okay, so should I run through that again? Was that a little fast? Let's do that again. So if I know that I to the 1 is just I, what's I squared? Well, if I want to come up with what I squared is, I'm just squaring what is I really equal to, right? I stands for the square root of -1. So I squared is the square root of -1 squared, right? And so look what happens. The square root is canceled by squaring it, and I just get -1. I squared is -1. If I want to simplify I cubed, well, I'm just going to use some properties of exponents here, right? I know that a to the m times a to the n equals a to the m plus n, right? So I could say I cubed is the same as I to the 2 plus 1. I could rewrite that as I squared times I to the 1, couldn't I? Because when I multiply like bases, I just add the exponents. So I squared times I to the 1 is I to the 2 plus 1, which is 3, right? That's a convenient way for us to break it down because I know that I squared is just -1. So -1 times I gives me -I, right? And then I to the 4th, I could write that. I know that a to the m to the n equals a to the m times n. If I take a power to a power, I multiply the exponents, right? So I squared would be I to the 2 times 2, which is equivalent to I to the 4th. I squared is just -1, so I'm really just squaring -1, which is +1, okay? So I get this pattern. There's my pattern for I to the 1 through I to the 4. Now, what we're going to see here is that for values of I bigger than that, the pattern is just going to repeat, right? Because I to the 4th, or excuse me, I to the 5th, I could rewrite as I to the 4th times I. Well, I to the 4th is just 1. So I to the 5th is the same thing as I to the 1st, right? What about I to the 6th? I could rewrite that as I to the 4th times I squared, but I to the 4th, remember, is just 1. So it's equal to I squared, right? And we know what I squared is. I squared is -1, right? I just get 1 times -1, so it's -1. Look at that. The pattern, it just continues, doesn't it? I to the 7th is I to the 4th times I cubed, so it's just 1 times I cubed. It's going to be the very same answer as I cubed. It's -I. And I to the 8th, I could just write as I to the 4th squared if I want to, right? So 1 squared is 1. So this thing is just going to cycle in patterns of 4, the powers, right? Everybody see that? Like if I did I to the 9th, I to the 10th, I to the 11th, and I to the 12th, it's just going to cycle through that same pattern again, isn't it? Right? It just keeps repeating. And so the powers of I are pretty easy to deal with. We can either think of them as going in fours, or even more easily, like if I want to do I to the 15th, I just have to use the same strategy, right? Like I could make I to the 15th. I could make that I to the 14th times I to the 1, couldn't I? Everybody agree? Why do I pick 14? Because it's even, right? So I to the 14th, that'd be the same thing as saying I squared to the 7th, because 2 times 7 is 14. So once I come up with an even power of I, then I can always write that as a power of I squared. And I squared is just -1, right? So I have I squared to the 7th is I to the 14th times another I. Well, that's just giving me -1 to the 7th, because I squared is -1. -1 to an odd power is negative, right? That's -1 times I is -I. Everybody see that? See that trick? We're always just going to rewrite these big powers of I in terms of small powers of I that I can deal with, right? That I know. What about I to the 62? Well, that's even. I could just write that as I squared to the 31, couldn't I? Right? Because if I take a power to a power, I multiply the exponents, right? So 2 times 31 is 62. So this is just equal to then -1 to the 31. A -1 to an odd power is -1. -1 to an even power is 1. Okay? Tricky, huh? Let's maybe look at one more of these. Let's look at something like this guy down here, number 18. Okay, and you can see these are just on your notes template if you want to be going through this with me. But that's all right. I'm going to publish these. These will be online as notes here today, right? So you can just look at this PDF if you want to. So I've got the quantity I times the square root of 3 squared times the quantity -8I squared. Well, here's another property of exponents that you'll probably recall from Algebra 1. If I take a product to a power, that's just equal to the individual factors taken to that power. So the product A times B to the n equals A to the n times B to the n. It's kind of effectively what you're doing is now this won't work if I'm adding, right? This only works if I've got a product. If I'm multiplying things and that the product is taken to a power, then I can effectively just distribute that exponent to both of the factors, right? Okay. So I can do that for both of these cases down here, correct? Here I've got the product of the number I times the square root of 3 squared, right? So then I can write that as the square root of 3 squared times I squared. Doesn't matter the order, does it? I put the I squared at the end. I could have just left it at the start. So I'm squaring both of those. I'm squaring the I and I'm squaring the square root. Same thing over here. I'm squaring the -8 and I'm squaring the I. And I've got the product of all of those things, right? Well, we know I squared is just -1. If I square a square root, it cancels the square root, and -8 squared is 64. So now I've just got the product of those normal numbers, and that's easy to, right? Take a product of a bunch of real numbers. Okay? Give me 1 to 5 on that. Okay? Just takes a little practice. This first assignment is really going to be just about this kind of stuff, just getting familiar with powers of I, simplifying negative radicals. It's kind of a warm-up for the other stuff we're going to do. Okay? Do you want to go through another example of this? You guys let me know. I will happily go through any of these other ones. You let me know. You want to go through any of these other guys here? Okay. Should we do how about number 20? That sound good?
Can you go real quick back to the first page that says imaginary numbers?
Sure.
I didn't get blanks.
Oh, yeah. To that page right there?
Yeah.
Okay. Maybe something I'll add to this page too. just to really reinforce this, because this is a really big one for us. And that is that, whoops. Let's see. Okay, there we go. Right, that's another thing we want. I'm going to put that in a red box because that's another thing that we just want to always remember, that I squared equals -1 because we're squaring that square root, which cancels it. Oh, darn it. There we go. Okay. All right. So we were going to do number 20. Okay, so number 20 here. I could break this up into, there's a bunch of ways I could do this. So one thing I could do is I could split this apart into the square root of -1, which is I, times the square root of 24. I'm going to put the I out front. Sometimes it's better to put the I's in front of radicals, because if I put the I at the end, it's a little confusing. Does the I go inside the radical or outside the radical, right? So a lot of times it's just more convenient to put the I's in front of radicals. Okay, so there's how the first one breaks up. This guy right here is going to break up into times I times the square root of 3 times I times the square root of 2, right? And so if I reorganize all that stuff, that just equals the square root of 24 times the square root of 3 times the square root of 2 times I cubed. Okay, well, what's I cubed? Everybody type it in chat. What's I cubed? It's just I squared times I, right? So what's I cubed? Yeah, good, -I, right? So I know I'm going to get a -I here. And now I've just got to simplify all this stuff. Well, we could, if we're using the Desmos trick, I could just multiply 24 times 3 times 2 and then use the Desmos trick. But let's go ahead and use couples go out, singles stay in on this one. Let's use a factor tree. So I've already got this thing factored into, it's broken apart into the numbers 2, 3, and 24. Well, those are both prime. I've just got to break the 24 down, right? So 24 I could break down into 3 and 8, right? 8 I break down into 2 and 4. And 4 I break down, I'm all the way at the bottom, huh? 4 I break down into, 2 and 2, right? Okay, so let's gather these up then. I've got a couple of 3s, couple of 2s, and another couple of 2s, right? So this simplifies the square root of 24 times the square root of 3 times the square root of 2. I've got only couples, right? So I don't get anything stuck in the radical. Outside, I'm going to get 3 times 2 times 2. There's a couple of 2s, right? So I end up getting 3 times 2 times 2 times -I. Well, what is that? The negative, positive times positive times positive times negative is negative. So I get a negative value. 3 times 2 times 2 is 12 times I. There's my answer, right? That makes sense? The only part that's any different, you guys did a problem just like that, only you didn't have the negatives in there. When we did the assignment on simplifying radicals, remember we did an example just like that without the i's. The only difference is the i's. Okay. Okay. So these imaginary numbers are part of a larger set of numbers called complex numbers. Okay, and we're going to talk more about this here in a second. I'm going to give you a diagram that illustrates these relationships. But the set of complex numbers includes all possible numbers, right? Real numbers are a subset of the set of complex numbers. Earlier in the year, we broke down the set of real numbers into rationals and irrationals, and then the rationals we could break down into integers and whole numbers and natural numbers, right? But all of that stuff, the entire set of real numbers, they are really a subset of this larger set of complex numbers. Complex numbers can always be written in a standard form, which looks like this. They're written in the form a plus b times I, where a is what we call the real part of the complex number, and b is what we call the imaginary part. So for real numbers, all the numbers you've ever dealt with are complex numbers that have a value of the imaginary part equal to 0, right? Because no i's have ever showed up in any of the numbers you've dealt with until today, right? So for all those numbers, the value of b was 0, and the value of a was just any possible real number, okay? For the pure imaginary numbers, well, in that case, the real part would be 0. All these numbers we dealt with on these previous, like right here, right? When we simplified those values, we ended up getting a pure imaginary number where I just end up with some real number times I, right? So all the imaginary numbers we've dealt with today have been pure imaginary numbers where the real part has been 0. But in general, for a complex number, typically neither one of those parts are equal to 0. Usually there's a real part and an imaginary part. For example, if we take this number 5 plus 2i, that's a complex number in standard form where 5 is the real part and 2 is the imaginary part. Okay, so what about this example right here then? 3 plus 7i. Type in chat for me, what's the real part? Everybody type it in real quick. Let's make sure everybody, yeah, it's 3, isn't it? Good. Okay, so the real part is 3. What's the imaginary part? Type that in. Okay, yeah, and the reason I'm making you do this, so the imaginary part only includes the 7. Okay, the imaginary part is the number that's multiplied by the I. This is the pure imaginary number that's added to the pure real number to create the complex number. When we talk about the real part and the imaginary part, those are just the values of A and B respectively. You'll see why here in a little bit, okay? How about this next one here? What's the real part of the complex number 2i? Yeah, it's 0. Good. 0. Okay. And we could, really technically this is the complex number 0 plus 2i, but we don't say 0 plus, do we? Right? We just say 2i. And the imaginary part then would be 2, wouldn't it? Okay. So if we look at the relationship between these numbers, here's one way to visualize it, right? So we've got these complex numbers. In standard form, they have a real part and an imaginary part. So if we look at the set of all numbers, the set of complex numbers, those are the set of all numbers written in the form a plus bi. A subset of that would be where b is equal to 0, we get the set of real numbers like we just talked about. And another subset would be where a is equal to 0, we get the pure imaginary numbers. Okay, and within this set of real numbers, that entire Venn diagram that we looked at the beginning of the year with all those subsets of real numbers would be included in that green circle right there. Okay. Everybody got that? Give me 1 to 5 on that real quick. Okay. Okay. Here is a more sophisticated look at that. There's a lot of stuff here that's going to be kind of above and beyond, the scope of our discussion today. But this is really pretty cool, actually. You can take this set of complex numbers and you can subdivide it in all kinds of interesting ways, right? Like we could say, for example, the set of pure imaginary numbers, here it is, right? The set of pure imaginary numbers. And we could take the set of pure imaginary numbers that have irrational coefficients. We could take the set of imaginary numbers that have rational coefficients, right? That could be rational numbers. They could be what we call algebraic numbers. They could be integers. They could be natural numbers. We can take the set of pure real numbers down here. This is the set of all pure real numbers, and break those up into natural numbers and integers and rational numbers and real algebraic numbers, which we'll talk. That's a different. That's above the scope of this. That's more of like a math theory topic that you talk about in college. And then the set of irrational reals also, right? Sometimes we call the set of irrationals transcendentals. Everybody see this? So it's pretty complicated, but once again, this is, you don't have to really focus on all those little intricacies. That should hopefully be exciting for you, though, as young math students, that there's still, even when we're just talking about something as simple as numbers, this isn't even algebra, right? This is just numbers. There's still all these different avenues you have to explore, even just ways to discuss numbers, right? But bottom line, the set of complex numbers is the superset that contains them all, right? Every number falls in there. Okay, so let's just practice this a little bit more, okay? So I want you to identify the number -4 as real complex, pure imaginary, or non-real complex. And more than one of those could apply. Okay. So let's just go down that list and you give me a thumbs up or a thumbs down on all those options A through D. Is the number -4 pure imaginary? Thumbs up or thumbs down? Seeing lots of thumbs downs. How come it's thumbs down there? Abby, why is it thumbs down?
Because it's not an imaginary number.
Yeah. Yeah, there's no I, is there? No, good. There's no I. So there's one that we can definitely cross off, right? That's not one of our answers. Is it a non-real complex number? Every number is a complex number, right? But is this a non-real complex number? Thumbs down. Thumbs down, definitely, right? How come? Andrew, how come?
Well, is it because it's a real complex?
Yeah, because it's real, isn't it? Non-real means it would have to have an imaginary part, right? There's no I's, so it's not non-real complex. Is it complex? Thumbs up or thumbs down? Yes, it is, right? How come it's complex, Rebecca?
Because it can be put in that form of A plus B times I.
It is. It can be put in that form. And in fact, every number is complex. So by default, that's going to come up on, that's always going to be a checked box for us, isn't it? Every number is complex. So that one's checked. Is it real? Thumbs up, thumbs down? Yeah, pretty obviously -4 is a real number, right? It's an integer, which is a subset of the real numbers. Okay, good. Let's try this next one. Same issues. 5 plus 6i. Is that real? Thumbs up, thumbs down? Yeah, definitely thumbs down. It's got an I in it, right? So it's not real. Is it a non-real complex number? Yeah, it is, right? It's non-real because it has an I, and it's all numbers are complex. Is it pure imaginary? Thumbs up or thumbs down? Good. Thumbs down, right? Because it has a real part, doesn't it? Remember that a pure imaginary number has no real part. A would be equal to 0, right? So not a pure imaginary. Is it complex? Yeah, everything's complex. All numbers are complex numbers. Okay, how about this one? Last one. Negative 4i. Is it pure imaginary? Thumbs up or thumbs down? Is it pure imaginary? Okay, what are the values of a and b for that number? For negative 4i. What's a equal to? 0, right, okay. B is negative 4, right? Well, what's the definition of pure imaginary? It's any complex number where a is 0. So this is pure imaginary, right? It's pure imaginary because it has an I, but it has no real part. Everybody agree? Okay. So it is pure imaginary. Is it complex? Yeah, every number is complex. Is it a non-real complex number? Thumbs up or thumbs down? Yeah, thumbs up. It's got an I in it, right? So it's non-real. Is it real? No. It's got an I, so it's not real. Okay, good. Okay, last one. I forgot I had one more in here. Okay, is it non-real complex? Yeah, because that does have an I, doesn't it? Right? Isn't that just 2i? Everybody agree? So it is non-real complex. Is it pure imaginary? Yes, good. Thumbs up, definitely. Yep, good. Because there's no real part. It just simplifies to 2i. Of course, it's complex, and it's not real because it has an I. Okay, so now let's start to focus on, and by the way, we've covered everything for that first assignment. Okay, I'm just going to keep going though, and then we'll just pick up next time wherever we leave off. So adding and subtracting complex numbers is super easy. It's literally like you are adding like terms. That's it. Just think of the I like a variable, and you're adding like terms or subtracting like terms. It's exactly that simple. So let's look at one example of each. That's all it takes. How about this one right here? Okay, well, what am I doing? If I look at like terms here, I've got two numbers that are real, pure real, and I've got two numbers that are pure imaginary. I'm just going to add up the like terms, add up the real numbers and add up the pure imaginary numbers. And I get negative 11 plus 9 is negative 2 plus 3i plus 2i is 5i. That's it. How simple, right? You got it. You know everything you need to know to add any number of complex numbers. You just add up the real parts and the imaginary parts as like terms. How about subtracting? Same issue, right? How about this one down here? We'll look at number 4. If I'm subtracting, what would you normally do if you're subtracting if that were an x? Wouldn't you just distribute the negative sign and add, right? Everybody agree? That's how we would add this stuff. If these were x's instead of i's, we would just get 6i. If I distribute the negative, I get minus 14 plus I plus 5 minus 3i. And then I'm just going to add up the like terms. Well, there are my real parts I can add up, right? So I'm going to get negative 14 plus 5 is negative 9. And then I'll add up the imaginary part. 6i plus I is 7i minus 3i is 4i. Okay, we good? No big deal. I'm not going to spend any more time on that stuff for you guys. That's all you need to see. What about multiplying? Okay, multiplying is also really simple. Okay, there's just one little trick we got to remember when we multiply, though. We have to remember that I squared is equal to negative 1. And we're going to multiply exactly the same way we would if we were dealing with x's, except that whenever we end up with an I squared, we have to convert that to a negative 1. Okay, so let's take this example. Well, it doesn't matter which one. Let's just take the example. How about number 8? So if I'm going to distribute here, I'm going to distribute the 2, let's say, to both parts, and I'm going to get 2 times negative 5 is negative 10. 2 times negative 3i is negative 6i. Let's distribute the negative 4, right? And I'm going to get negative 4i times negative 5 is plus 20i. And then negative 4i times negative 3i would be positive 12i squared. Everybody agree? Okay, but anytime we see an I squared, what are we going to trade that for? What's I squared equal to? Type it in chat. Negative 1. Good. Okay. So really all that does is it's just going to change. We're going to cross the I squared out and change the sign of that term to a negative, right? And now when I add up the like terms, what do we get? So I've got a negative 10 and a negative 12 here that are going to add to negative 22. And then I've got a negative 6i and a positive 20i that add to 14i, right? There it is. Okay, no biggie, right? Adding, subtracting, and multiplying complex numbers it's really very simple. And we won't even do this one. I mean, you guys will be, all we'd have to do here is follow order of operations, right? What would we do first? We're going to multiply these guys out. I'm going to multiply these out and get an answer, right? So I'm going to have to simplify that down to a complex number, something in the form a plus bi. And then whatever I get there, I'm just going to subtract. Well, I'll distribute the negative, won't I? Let's go ahead and distribute the negative. So I'll get a minus 4 minus 2i in combined like terms. Right, but we probably don't need to do that example for you guys. You'll have no problem with that. What about something like this? Okay, if I've got an algebraic expression like x squared minus 7x plus 6, let's say that's f of x, right? Let me write this a slightly different way. So here's f of x. And we want to evaluate this at the complex number 4 plus I. Well, that's all right, right? We can do that. Complex numbers are just numbers. We can do all the same stuff with complex numbers that we can do with regular numbers. So I know we got to go here, but I just want to show you this one thing. So if I evaluate this at 4 plus I, whoops. Then every place I had an x, I'm just going to plug in a 4 plus I just like I would and simplify, right? How do I square out a complex number? Well, for now, let's just write that as a product, 4 plus I times 4 plus I, right? And I can do all that stuff. That's just multiplying and adding and subtracting complex numbers. Okay, so you should be good. That'll get you through quite a bit of stuff. Get you through the first assignment for sure. Okay. All right. Hey, I'll be here after school if you need me for anything. Otherwise, I will see you next Tuesday. Have a great weekend.